Hey everyone, I'm James Codella. I'm a product manager in Azure Cosmos DB. Today we're going to talk about how Microsoft powers semantic similarity search in some of the largest applications in the world using Microsoft DiskANN, a unique vector index that was developed right here at Microsoft. Now, before we get started, let's have a quick recap on what approximate nearest neighbor search is with vector search. So imagine that you have a database with hundreds of thousands or even billions of documents, and you create vector embeddings or representations of these data using a AI model like one from Azure OpenAI. Then your dataset's primed to do vector similarity search, where you can have a query or a user question, and you can conduct similarity search against all those vector points to find the documents that are most similar to that question. So traditionally, you might want to do an exact search and search over all documents in the database, but this becomes really slow and intractable at scale. Instead, we use approximate methods and approximate nearest neighbor search and make a trade-off between the recall or accuracy and the speed of the search. Now, in Microsoft, there's a lot of really unique sort of scenarios, right? There's between the cloud environments or cloud applications from web search and ads and recommendations to enterprise scale email search and Outlook to document search and even edge applications like Windows Copilot. There's a variety of different index sizes. That means that we have to be able to search efficiently no matter what the size or scale of the application or the use case is. Many of these applications also experience tons and tons of updates, so insertions or deletions of vectors into the vector index itself. And so we need a solution that's able to provide robust results and high accuracy results, even though there's modifications to the index itself. And finally, we need to be able to have really low latency search and handle high throughputs for the scale of these massively popular applications. And so traditionally, this has been a challenge for a lot of vector indexing technologies. The demands inside Microsoft spurred the need for a new type of vector index, and this started the DiskANN project. And DiskANN aims to solve multiple problems. The first is that traditional in-memory vector indexes tend to be expensive at scale because they need a lot of memory. DiskANN leverages compressed vectors that are stored in memory, but then uncompressed vectors on a graph data structure on high-speed SSDs to be able to do cost-effective vector search at any scale. The second problem is a lot of updates, insertions, modifications, and deletions to the vector index tend to make the performance degrade. That is, the accuracy can degrade over time, and so typically require a full index rebuild, which can also be computationally expensive and take time. The third problem is most vector indexes are not designed for filtered or hybrid queries, and so this could result in low recall or high query complexity or latencies. In comes Microsoft DiskANN. As I mentioned, it's a technology that was developed at Microsoft Research, and we're really excited that it's in Azure Cosmos DB as generally available for our vector indexing and search capabilities. The way it works is when you insert vectors in Azure Cosmos DB, we compress the vectors through product quantization, and these compressed vectors are kept in RAM of the Cosmos DB backend for fast access. The uncompressed vectors are used to create a complex graph data structure. These uncompressed vectors and the graph are stored on high-speed SSDs, which make up the backbone of the Azure Cosmos DB architecture. There are algorithms in DiskANN that make it really efficient at building the graph and also pruning the graph so it's very easy and cost-effective to search and has fast convergence of search. So combined, this makes vector search in Azure Cosmos DB very, very cost-effective. It leverages the unlimited scale capacity of Cosmos DB as well to provide low latency, robust vector search at scale. Now, Azure Cosmos DB is actually very well suited for vector search scenarios, right? It offers very flexible data modeling, right? So it's a NoSQL database, so you don't have to worry about a fixed schema. And we have tons of customers that are storing chat history, agentic memories, user interactions, but also e-commerce data or transactional data, operational data that's scanned from PDFs and images of the sort of operational data that comes from other applications. So there's really a lot of flexibility there. Furthermore, Azure Cosmos DB for NoSQL is enterprise ready. It features high elasticity and hyperscale, 5 nines of availability, low latency point reads and writes, continuous backup and restore for disaster recovery, multi-region and geo-replication, and also all the security features that you've come to know and love from Azure, such as virtual networks, customer managed keys, and RBAC policies. Cosmos DB also features a lot of usability and functional deployment methods that make it really powerful for any application that you develop, from a serverless model, so pay as you go or pay as you use, to a provision model with instant and dynamic autoscale capabilities. It also features many levels of built-in multi-tenancy, a SQL-like query language that's very powerful for getting the data that you want, and also offers multiple consistency levels. So combined, Azure Cosmos DB for NoSQL really is the best vector store for any of your AI application needs. Being able to store your vector index and your vectors together with your original data is a game changer. It removes the need to ETL your metadata into a dedicated vector database. You can keep your vectors and your data together, and it will simplify your application architecture and reduce your costs. Because of the flexibility of Cosmos DB's query syntax, you can add any query filters that you'd like that are supported in the Cosmos DB SQL syntax to your vector searches. So you can perform filtered vector search at any scale. We also offer multiple vector indexing options, from flat for exact search, quantized flat, so exact search on compressed vectors, and then finally the DiskANN index, which is really great for applications at scale. And we have thousands of customers today building a diverse range of scenarios, all powered by their data stored in Azure Cosmos DB. Storing operational and vector data together, as I already mentioned, is a huge value proposition for these customers. Built on top of this, many customers do retrieval augmented generation, leveraging vector similarity search in Cosmos DB natively. Cosmos DB is also very popular as a conversational history store for agentic memories, for conversational context, and for LLM optimizations that you can use later on. Semantic caching builds on these two concepts, where you're storing conversational histories in Cosmos DB, and you can leverage previous responses from the large language model, doing a simple vector search rather than feeding more data to the large language model. This saves you in token consumption costs, so API calls to your large language model, which reduce overall cost and can save on the latency in your applications. And of course, all of these are very applicable to AI agents as well. Multi-agent scenarios need to retrieve data, need to store data, need to save a checkpoint or statefulness of the agent, of the agents and the agentic applications. So Cosmos DB is a great storage layer for these transactional workloads, as well as for retrieval augmented generation. Now, let's take a look at some examples of vector search in practice in Cosmos DB. So executing a vector search in Cosmos DB is really simple. As I mentioned, vector search is part of our query syntax, right? So performing a simple vector search is pretty easy. In this example query here, I'm selecting the top 10 most similar documents. I'm projecting a name field. I'm also projecting the vector similarity score and I'm giving add score, so I'm giving score as an alias from C for my container, and I'm ordering by vector distance. So the order by vector distance is really important. This sorts the results in order of the similarity score from most similar at the top to least similar down below. If I want to do a filtered vector search, I can just add a where clause, just as I would in any other query. It's just that simple. I could even do customized search, leveraging DiskANN, right? So I could, in this example, select the top 10 documents, and I'm going to project all properties of those documents. I'll add a filter as well. And this time I'm saying order by vector distance, and I'm giving the property that contains the vectors of my documents. I'm also giving the query vector, the thing I want to compare against. I'm saying false here. So false or true. False means that I will use the vector index, and true means I want an exact search. And then in this object here, defining a search list size multiplier. So this is a hyperparameter of my search. Basically, if I want my search to execute faster, I can lower this number. If I want my search to be more accurate, I can increase this number. And this finds more candidate vectors in the vector search itself. And so there's that trade-off, right? Just in any approximate nearest neighbor search, there's always a trade-off between latency and accuracy. So this is a really easy parameter for me to tune if I want a little bit more accuracy in my search, or maybe a little bit lower latency in my searches as well. Now, let's take a look at some numbers. So these charts show query latency and the RU charges for vector search on the Wikipedia Cohere embeddings dataset, right? So these are 768 dimensional vector embeddings that are created from the Cohere embeddings model. And on the left, we can see the latency, so milliseconds on the y-axis, and we can see the P50, P95, and P99 latencies here. So we can see different scenarios as well. We can see for 100,000 vectors, 1 million vectors, and 10 million vectors. So what's really interesting is we can see that the vector search is actually really nicely bounded, right? The latency is quite low. 10 million vectors in under 40 milliseconds, that's really amazing. On the right-hand side, we can see the corresponding request unit charges for executing a vector search. So we, at the P99 level, we have 100,000 vectors. A search on this costs about 30 RUs. And at the 10 million scale, it costs about a little over 70 RUs, right? So this is really amazing. We're going like 100 times more vectors that we're searching against. And yet the query cost only practically doubles, a little bit more than doubles, right? So this is really amazing. We can be really robust against very large scale vector searches, right? Because of the efficiency of DiskANN and the Cosmos DB architecture. Okay, let's take a look at some of the costs for the scenario. So imagine that you're inserting 10 million vectors of 768 dimensions into Azure Cosmos DB for NoSQL serverless. Then we're going to perform 1 million vector searches on this data. So the insertions of these vectors at 25 cents per 1 million RUs in the serverless model, and at a cost of 65 request units per insert, brings us to about $163 to upload all our data into Cosmos DB. Our storage cost, 25 cents per gigabyte per month, amount to about $23 per month. Then we conduct 1 million vector searches at about 60 RUs per search. This is roughly $15 for a total cost of around $201. That's incredibly cheap for vector search on Azure Cosmos DB with all the great enterprise-ready features that you get in a globally distributed database like Azure Cosmos DB. Let's see how this scales also. So here we have some plots on vector search from the MS Turing dataset. On the left-hand column, we have a scale of 1 billion vectors. And in the right-hand column, we have a scale of 100 million vectors. The top charts show latency, and the bottom charts show request units. And what we can do is we can see the latency on the server side in blue, or on the client side in green, on a spectrum of different scenarios where we're increasing L search. So this is that search list size multiplier I mentioned, right? So we're basically changing this to get higher recall at every step. So we can see that L search is 50, so relatively fast. We can see that the P99 latency on a billion vectors is under 50 milliseconds on the Cosmos DB backend, maybe around like 75, 80 milliseconds and on the client side. That's really, really fast for a billion vectors, incredible. Now, as we increase L search, we want to increase the accuracy. We can see that the latency also increases. But even at an L search of 200, which gives us a recall of nearly 94%, we still have our P99 server-side latency of under 100 milliseconds and our client-side latency as at around 140 milliseconds. That's super, super fast for vector search on a billion vector scale. And we have even more optimizations in the pipeline to bring those latencies down even further. We're really excited. Okay, so speaking of optimizations and new features, what's actually coming next? So we have performance improvements that are continuously rolling out to both DiskANN and the Cosmos DB backend to make your vector searches at scale even more cost-effective and faster. We're also giving you the ability to configure and change your vector indexes so you can do experimentation on what's right for your unique scenario, or you can modify it as your scenario scales. Coming soon, we're also launching what we're calling sharded DiskANN. This is really powerful. This allows you to create essentially unique vector indexes, so unique DiskANN graph, for every property value of a document. So imagine that you have maybe a tenant ID specified as your shard key or a particular category. Then you can isolate your vector search to just that category or just that tenant. This makes the vector search much faster, more cost-effective, and also have higher accuracy. We're soon also launching filter DiskANN, which leverages new algorithms for improving vector search with query filters to make them faster and more cost-effective. You may also already know that in Cosmos DB, in addition to vector search, we also have full text search and ranking that allows you to search using a full text index for keywords and terms. We're soon adding a lot more features to this, and we're really excited that we're going to be announcing the general availability of full text search and ranking in Azure Cosmos DB at the Microsoft Build conference at the end of May. So we're really excited. There's going to be some really great new features that are coming along with it. So join us at Microsoft Build to learn more about that. We also have hybrid search in Azure Cosmos DB. So this is a combination of the vector similarity search and the full text scoring to bring you even more relevant search results. Again, it's really easy to execute in our query language. And this is also going to be generally available at the Microsoft Build 2025 conference at the end of May. We're also excited to be teaming up with the Microsoft Logic Apps team, right? So everybody knows Logic Apps, a very powerful resource in Azure for these workflows that you want to operate continuously with very low latency. Well, we're taking it to the next level by building templates that allow you to do document ingestion and processing. So essentially being able to do OCR and extract information from documents in blob storage or on SharePoint, process the data, chunk it, create vector embeddings from those chunks, and then insert them into Azure Cosmos DB for vector and full text search. This is going to be really powerful. Any operational data that you have in blob storage or SharePoint, you can be rest assured that it will be searchable in Azure Cosmos DB and stored there securely. Now, you may be wondering how you can get started with vector search, or where can you go for some samples? Well, the good news is we have a fantastic samples gallery. If you go to aka.ms/Azure Cosmos DB/gallery/AI, you can get started and take a look at our samples gallery that's filtered just for generative AI scenarios and samples. And you can find everything from examples of managing chat history in Cosmos to managing vector search and RAG, and even multi-agent applications with examples in Swarm, LangGraph, and Semantic Kernel. And if you've never used Cosmos DB before, you can get started from free. Just check out aka.ms/trycosmos, and you can get started on a lifetime free tier account. And you can do vector search on that free tier account as well. So really a lot of great options for you to get started and to use Azure Cosmos DB for your AI applications.